Okay, so before I talk about the properties of the definite integral, I realized that I made a mistake in this last portion of this problem. So right here, when I pulled the 81 over 4 out of this limit, I left another copy of the 4 in there. That should not be there. So I'm going to go ahead and fix this. So this should just be n squared plus 2n plus 1 over n squared. And the limit of that is just going to be 1. So we will get just 81 over 4 minus 27. And so that will change this answer. I thought that the answer was a bit strange. So fortunately figured out what the mistake was. And we can go ahead. This is a bit easier to compute. We just need to do 27 times 4, right? And so we should get 81 minus 108 over 4, and then just do this here. We should get negative 27 over 4. And that will be our final answer. Okay, so now that we've taken care of that, let's talk about properties of the definite integral. And so these are going to be very useful things to know. So the first one is that the integral from a to b of a constant function, so a function that's just equal to c, that is equal to, well, it's best if we just try to picture what's going on. So if this is our value c and our function is constant on the interval a to b, then since we know that this definite integral gives the area under the curve, this is just a rectangle, right? So we can compute the area. That is going to be a rectangle with width b minus a, and actually need should write this a bit lower. So it is width b minus a and height c, so you get c times b minus a. Right. Okay, and so that's our first property. Second property is if we have a, the integral of a function over an interval a to a. So this is if the top bound matches the bottom bound. Right? If that happens, then if we think about what this might look like, so we have some function we have some function f, and we're talking about the area under the curve over an interval that has 0 width. So an area of a rectangle with 0 width is just 0, right? So it kind of makes sense that this would be equal to 0. So if you have an interval that is degenerate, this is what we call this, when the right endpoint equals the left endpoint, then you get that the interval is 0. Okay, and then this one is pretty, I wouldn't say self-explanatory, but it's what you would expect out of this type of thing. So integrals inherit a lot of the properties from sums. They are defined using sums, the Riemann sums. So we do get that this property where the integral of f plus g or the integral of f minus g is equal to the integral of f plus the integral of g. One thing I'll point out is that whenever I split this one integral into two, whenever you write the integral sign, you should have a dx that closes the integral. So one function that the dx provides is to tell you what the variable is, and another function that it provides is to tell you where the integral stops. So you can think of these as like opening and closing parentheses. So if you have an open parenthesis, I guess, you need a closing one as well, right? So don't forget the dx on the ends. Okay. And then similarly, this comes also from properties of sums. We can, if we have c times a function, we can pull that constant out. And so this is similar to how limits work as well, right? And derivatives for that matter. So this is a common property, and it works as well for integrals. So we get this. And then this next one is a little weird. You might think it's a bit strange, but it does happen sometimes. So here, if we have the integral of f of x from b to a, that is equal to negative the integral from a to b of f of x, right? So the reason that this works out this way, so what happened is when we switch the bounds, so we just changed from b to a to b, we switch the bounds, we have to multiply by a negative. And the reason this works out this way, just completely ignoring that clearly either a is less than b or b is less than a, so one of these is sort of the correct orientation and one of them is not. But in any case, even if we don't know which one is less than the other, we can still compute the Riemann sum, and what will happen is in the first case, so I'll just label these with numbers, so this is the first integral, this is the second one. So in 1, delta x will be equal to, so we have the interval from b to a, that will be a minus b over n, and in 2 we have delta x is equal to, that one is in the normal direction, so b minus a over n. So see that this is equal to negative b minus a over n. This is where the negative comes from. This is where it's introduced into the Riemann sum, and then working all the way through, which honestly doesn't take that long, but I think I'll skip over it now. You get that you just get the negative of the same exact limit. Okay. And then we have one last one, which I think I can fit on this page, so the next page is unnecessary. And this one is really useful, and it really helps to visualize it to in order to remember this one. So if C is a number between A and B, where A and B are your endpoints of your interval, then what you can do is you can think of, so here's our function from A to B, and C is some point in the middle. You could split this into two pieces, right? And then you could write down an integral that describes the area over the interval A to C. That would be the integral from A to C of f of x dx, right? And then you could write down the area of the second part, and that would be going from C to B. So your bounds would be C to B, integral of f of x dx. So here, we get that when we add these two things together, we get the first integral. So the integral over the entire interval A to B. And this really comes in handy because sometimes there's a convenient place to split to make an integral a little bit easier to calculate. Like I said, it may not come up necessarily in this class, but definitely in the next class, in Calc 2, that is. Okay, so that is all we are going to cover for this section. Don't forget to do the comprehension check question.